Okay, so there's a couple of things that I want to do this week. So by the way, I'm sorry that I didn't post this on Monday. I was having some technical difficulties that I think I'm now over. Okay, so I want to talk about change of variables. Change of variables is something that, it's one of these things that in principle seems simple, but then actually doing it in practice, at least in my experience, can get confusing for a number of reasons. One, I think just generally there's some confusion in it, just about what terms mean. Two, there's a lot of stuff going on. We have to use things like the chain rule and stuff like that, which again is one of these things that maybe is not complicated, but actually using it in practice can sometimes get complicated. But three, one of the things, sort of the underlying thing that I think makes a lot of this difficult is that there are some notational challenges that we have. For example, the prime notation, the Leibniz notation, they mean the same thing, but they can mean different things depending on the context, or it can get a little bit confusing knowing exactly what different notations mean. So let me just give you one example here of what I mean by challenge with notation before I start talking about changing of variables. So if I have a function, so let's say I have some function, and I'm actually going to use this function for several examples, so I'll just use it up here as something to keep in mind. Let's say we have some function f of xy, it's equal to e to the minus x squared plus y squared plus x cubed. Okay, now when I write something like the partial derivative of f with respect to x, this can typically mean one of two things. And when everything is like this, when everything's written in this way here, those two meanings are the same thing. The first meaning that it can be would be, I'm going to form the difference quotient wherever I see an x, and it's going to be the limit as h goes to 0 of f plus x plus h comma y minus f of xy divided by h. Like that's the one thing that it can mean. The other thing that it can mean, and like I said, in this case, I'm going to write down the same exact formula. I have the partial derivative of f. Another thing that it can mean is do the difference quotient, but in the first argument. So I'm going to replace the first argument with x, whatever the first argument is, plus h. In this case, it's just x. And like I said, we're going to get the same exact thing. We're going to get the limit as h goes to 0 of f of x plus h comma y minus f of xy divided by h. Okay. Now, where things begin to get a little bit confusing is when you don't have, so the reason things work here is because the only place x shows up is in this first component, and in the first component is just an x, and that's why things work well here. The way the genesis for where things can get a little messed up, or get a little bit confusing, I should say, is let's say I define a new function, g of xy, and g of xy is going to be something like f of 2x plus y, 3x minus 7y, something like that. So I have my f function defined here. G of xy is going to be equal to f of 2x plus y, comma 3x plus 7y. Now what this means is I'm going to look at my function f, and wherever I see like that first component, like what this means is whatever goes in that first slot, I'm going to substitute in here for x, and whatever goes in that y component, I'm going to substitute for y. Okay, that's just what function notation means. But now if you start asking questions like, what is the derivative of g with respect to x? Okay, things start to get a little bit confusing here. If I look at the formula here, again, both of these are going to match up, but then when I apply it to the f function here, I'm going to have to use the chain rule. And now these x derivatives mean two different things. So let me just sort of go through let's look at a slightly simpler notationally, simpler example here. Let's look at something like the derivative of f of 2xy, okay, and the derivative, I'm going to change it here as well. Okay, now in this notation here, wherever I see an x, I'm going to replace it with x plus h. And so I'm going to have f of 2 x plus h comma y minus f of 2x comma y over h. If I just mean to replace wherever I see an x in the difference quotient, I'm going to replace it with x plus h. This is what I get. Okay, now on the other hand, sometimes this just means take the derivative in the first component. If it means that, then whatever I have in the first component, I'm going to replace that with x plus h. And so I'm going to have f of 2x plus h comma y minus f of xy divided by h. Okay, so sometimes these notations, depending on the context, and you just have to pay attention typically to the context to know which one is meant here, both of these two things are equal to each other. Now what I'm going to do, what I think might be a little more helpful sometimes, is for this notation right here, I'm going to call this, at least in the context of changing variables, I'm going to call this d sub 1. Instead of d sub x, I mean d sub 1, meaning we're taking the derivative in the first component. Okay, and d sub 2 would mean taking the derivative in the second component. So this means like d sub x means when you form the difference quotient, wherever you see an x, put an x plus h. If it was a y, it would mean wherever you see a y, put a y plus h. Okay, and this here means in the first component, do the first component plus h. So whatever the first component is plus h, this is what you're going to get here. Okay, I think that little bit of different notation is helpful for when we start looking at derivatives like this. So for example, if I want to find the derivative of g with respect to x, let me use a different color. If I want to find the derivative of g, with respect to x, well, this is going to be the x derivative in this sense here of 2x plus y, 3x minus 7y. By the chain rule, what this is going to be, let me come down here. This is going to be the derivative of f with respect to this component. So that's going to be the partial derivative in the first component of f times the derivative of this with respect to x, which is 2, plus the partial derivative of f in the second component, so partial 2f of 2x plus y, 3x minus 7y, times the derivative of this with respect to x, which is equal to 3. Okay, now a lot of times when you see something like this, the notation here, and even like when I teach this in Calc 3, for example, the notation that you would have here would be something like partial sub x and partial sub y. That's a very common way to write that. But again, now you are sort of the partial sub x down here. If you write this with partial sub x and partial sub y, then the partial sub x here is different than the partial sub x there. And I think that for something, when I want to sort of work through something like change of variables, which in principle might be simple, but there's sort of these notational challenges, I want to be more explicit with what my notation means. So this video is taking a little bit longer than I thought it would be, so I'm going to stop here, and then in the next video I'm going to show you how we can use this change of variables thing to write the Laplacian and differential operators in general, in terms, to change from Cartesian coordinates to polar coordinates.